Hey folks, it's Professor Fiore. In this video, we are going to talk about the interaction between a bass transducer, a woofer, and the enclosure that it's in, right? The box. This is for direct radiator systems. There's two parts to this, really. There's some discussion on the transducer itself, and secondly, on the enclosure. These are sort of separate things that kind of come together to make the whole system, okay? So I want to take a look at this in kind of a big picture, right? Take a step back, look at the big picture. What's common? In other words, we're going to talk about things, whether it's, a little 4-inch woofer like this that you would find in a, like a little mini monitor, or kind of an entry-level little 8-inch woofer you'd find in a typical inexpensive bookshelf system, right? All the way up to maybe a much more beefy, say a 15-inch bass driver that's used for sound reinforcement systems, right? Quite a big range. But the physics is the physics. In other words, we're going to look at things that are consistent across all of these, and some things that people tend to, unfortunately, forget about. Sometimes people, in a rush, they look up some parameters on a loudspeaker. Maybe they have a spreadsheet set up or some software program, and they immediately start grinding out things, and they try to come up with, a home subwoofer or what have you, right? You can't ignore the physics. There's some important things going on here. First, let's take a look at the transducer. We can quantify the transducer with a series of parameters called Thiel small parameters. Now, this is named after Neville Thiel and Richard Small, two researchers who came up with some very important papers in the early 1970s, published in the Journal of the Audio Engineering Society. So the parameters of interest include FS, the free air resonance frequency, QES, the electrical Q, QMS, the mechanical Q, QTS, which is the total Q, not a simple addition of these, VAS, the acoustic compliance, Xmax, the maximum linear excursion, SD, the equivalent surface area of the diaphragm, PD, the power dissipation, and finally eta, the Greek letter eta, I'll stick it over here, which stands for the efficiency. So what do these things mean? All right, so one thing for me to just sort of throw out the terms, what are they? So FS is the free air resonance. This is the frequency at which the mechanical system wants to vibrate. Okay, so, like most mechanical things, right, this is a suspended diaphragm. It has a preferred natural resonant frequency. That's all FS is, right? The free air resonance. In other words, it's not in a box, it's just by itself, it's free air. Where does this thing want to vibrate? What's its natural vibratory frequency? Now, if you don't know what that is, it can be determined fairly easily, because at that point, there's an impedance peak at that frequency. If we were to plot the impedance of a loudspeaker, we see something that might be a little surprising. Right? This is the magnitude of the impedance. On the back of a loudspeaker, it'll say, oh, this is an 8-ohm loudspeaker, 4-ohm loudspeaker, 16-ohm loudspeaker. That's a nominal value. It's an average value. A typical woofer has a curve that looks something like this, right? So here's low bass, mid bass, and we work our way on up. It looks something like this. It's not just a flat line. 8 ohms would be like here somewhere, okay? That peak might be 30 ohms. This dip might be down at 4 or 5 ohms, and then it rises again. So this peak is due to the mechanical resonance, right? Actually, it's the interaction of all of these different parts, like the surround here, the spider that's inside, and so forth. This rise is due to the voice coil inductance that will have an increase in ohmic value and impedance as the frequency goes up. So this peak point is Fs, and you can find this experimentally quite easily. You just get a voltage source, an AC generator, frequency generator. Put a large resistor in series with it, like maybe a k ohm, 10 k ohm, somewhere in that range. That effectively turns the voltage source into a current source. And now, if you hook that up to the loudspeaker and you start sweeping the frequency around, you'll notice that the voltage goes up and down, right? The voltage across the loudspeaker goes up and down. And when it peaks, right, that will give you the Fs. So you're down here, you turn it up, the voltage will increase, and then hits the peak and drops back off, right? So that's where you would find your Fs, okay? Some of these other ones, like VAS, the acoustic compliance equivalent, basically what you're asking is, this thing has a springiness to it, okay? And VAS is basically the equivalent amount of springiness that you would get in air in a closed box, a sealed box, right? So whatever that works out to. Now, in customary US units, you would measure that in cubic feet. In metric, of course, that would be measured in liters. So you would say, oh, this is, 1.5 cubic feet is VAS. So the springiness of this would be equivalent to the springiness or the restoring force of air that's trapped in a 1.5 cubic foot box, okay? All right, Xmax is the maximum linear excursion. How far can the cone move before we start to see a lot of distortion, right? There's limitations. I mean, this cone can only pulse so far, right? So what is that maximum amount before we see a certain amount of distortion? That's what Xmax is. And there can be a very wide variation from loudspeaker to loudspeaker. For a mid-range, Xmax doesn't need to be very big at all. For a woofer, especially a subwoofer, Xmax very often needs to be a fairly large number, and you can find loudspeakers with an Xmax value of 20, 25 millimeters, right? Basically an inch. That's rather extreme. SD is kind of self-explanatory, the surface area of the diaphragm. PD, the power dissipation, right? How much power can the loudspeaker withstand, before it burns up, basically. You got to be careful about this when you're comparing loudspeaker A to loudspeaker B. You have to make sure that these things are measured the same way. And what we're looking for, the standard here would be what's called a RMS sine wave equivalent. Manufacturers can come up with other things. They might say, well, we have, peak impulse music power or some crazy thing like this. How does that relate back? I want everything to be measured with the same standard, right? So if I have one loudspeaker and it's rated at, 100 watts, sine wave RMS, and I have another loudspeaker that's rated at 200 watts, but it's, some kind of magical impulse music power or something, I can't say that second one has twice the power capacity because, what's the comparison between those two measurement standards, right? So you want to be consistent about that. And then the efficiency. Here's an important thing. Efficiency is not the same as sensitivity. People are used to a sensitivity measurement. So when you say something like, oh, I've got a loudspeaker and, 1 watt in, measuring 1 meter in front of the loudspeaker on axis, I get 90 dB SPL. That's a sensitivity measurement. That's not an efficiency measurement. Efficiency is the amount, the percentage of input electrical power that turns into output acoustical power. So just to use a simple number like 10%. If I have a loudspeaker that's 50 watt rating and it has a 10% efficiency, then we're saying 50 electrical watts in will result in 10% of that, or 5 watts out, 5 acoustical watts out. Okay? How is this different from sensitivity? Well, this measures the entire output all around the loudspeaker, right? It's basically everything. This is what we have available to us. Sensitivity is strictly on axis. It's what's right in front of the loudspeaker. Now, you can come up with ways of focusing the sound. For example, using a horn or a line array, you can sort of focus the sound in, kind of like a garden hose. Instead of being like this, it's like this. Well, if you can do that, if you can bring it together, focus it, you can get a higher sensitivity for the same efficiency. So although there is a correlation, in other words, speakers that tend to have high efficiency also tend to have high sensitivity, but it doesn't have to be that way. Again, we want an apples to apples comparison. All right. So some things that are out there that people have misconceptions on. All right. All right. So the first one I'm going to look at is the free air resonance. A lot of people think that, if I'm going to make a low frequency system like a subwoofer, I want to get the lowest possible FS as I can, right? That, the idea, the false idea is that given two loudspeakers, the one with the lower FS is going to be the one that has a deeper bass, a larger bass extension. It's going to go down deeper in frequency. Not necessarily true. That's kind of like saying, look, if I'm going to play basketball, height is an advantage, right? That's kind of an obvious observation. But it's not the case that if I would walk into a classroom and there's 20 people in the classroom, that the tallest person in that classroom must be the best basketball player, right? That's not the way it works because there's other things going on. Yes, it's an indicator, but by itself, it doesn't tell the whole story. So yeah, for deep bass extension, you generally want a lower FS, which you will get with transducers designed specifically for those applications. But by itself, it's not the whole story. There is an interaction with the system Q. There's an interaction with VAS. Okay? All those things come together. Second misconception. You want as much power dissipation or power handling as you can possibly get. Right? I want a loud woofer. I want the biggest, baddest, most monstrous thing going. So, I've got a 500 watt driver, a 500 watt transducer. Oh, my buddy has 1,000. Oh, what am I going to do, right? It's twice the power. By itself, it's not telling you the whole story. You really want to know what the PD is and the efficiency. So, as an example, I could have let's say a 200 watt loudspeaker, that's rated for 200 watts, and has an efficiency of, let's say, 4%. I'm going to compare that to a second loudspeaker that has a PD of 1,000 watts, but its efficiency is only 0.5%. Okay, so typical numbers, just so I'm not being crazy here, all right? A typical bookshelf loudspeaker probably has an efficiency in the neighborhood of 1%. If you want a ballpark number, 1%. Some are going to be higher, some are going to be lower, but that's a fairly typical number. Now, you get, a raw frame loudspeaker. Those are the kinds of numbers that you're going to be looking at for a woofer, all right? When you move into a professional loudspeaker, something that's designed for musical instrument amplification or, a PA like this beast, okay? Efficiencies tend to go up. So you might see something like for that loudspeaker might be 2%, 3%, 4%. The highest I've ever seen for that kind of loudspeaker is 7%. And that was actually a transducer that was designed to be horn loaded. But you're not going to see 25%. You're not going to see anything that high unless it's a system, for example, that's horn loaded. If it's a direct radiating system, no, these kinds of numbers are the sorts of numbers that you're going to see for efficiencies. But in any case, to get back to the point, you don't really care about the input power. What you care about is the output power. What's the acoustical output power? How many acoustic watts do I have? Not how many electrical watts are coming in. What's my output? Okay? Well, you get 4% of 200 electrical watts. In other words, you get 8 watts acoustic. That's your total output power. This, you get 0.5% of 1,000. That's only 5 watts. Well, if what I want is sound pressure, the 8 watts is going to be better than the 5 watts. That's simple. And there's other things going on here. I'd rather buy a 200 watt amplifier than a 1,000 watt amplifier because it's going to be a lot less expensive. It's also going to draw a lot less current from my wall socket. There's a lot of good things going on here if you can get efficiency, right? Efficiency is a big plus for the most part, all right? Okay, having said that, that's not the whole story, right? It's never the whole story. So even if you have something that is fairly efficient and you've got a decent power, once we get into really low frequencies, the limiting factor is going to be the X max. That's on the large signal, as we call it, the large signal limit, when the thing is really moving, when we start talking about mechanical limits, X max and SD, that product is going to be a really important parameter. The SPL that you get out of a loudspeaker is dependent on a parameter we call volume velocity, and you can visualize that in terms of this cone sweeping out a certain volume of air over time. So we have a surface area, SD, right? And we have a certain excursion, the biggest of which is X max. But we imagine this thing moving in and out. Okay, so if I take whatever that motion is, maybe let's say it's a millimeter, and whatever this area is, I multiply that, and that gives me the volume that this thing is moving on a single cycle, okay, out and back. Now maybe this is producing a 100 hertz tone. So it does that 100 times in 1 second. That total volume of air that you're moving relates back to the sound pressure level. If I reduce the frequency from, let's say, 100 hertz to 75 hertz or 50 hertz, something like that, it's moving slower, and the total volume of air that's going to be moved in that 1 second gets reduced, meaning the SPL is reduced. So if this thing is moving at 50 hertz instead of 100 hertz, to get the same volume of air, it's going to have to move twice as far because there's only 50 motions, 50 back and forth piston motions in a second instead of 100, right, at 100 hertz. So ultimately, when we get to low frequencies, it's the X max that's going to play a major role here because, of course, you can't change SD, right? Not dynamically. You can go to a larger loudspeaker, and that that increases SD, so you don't need as big an excursion. So for a given X max, right, you get more of that volume of air, right? So this guy compared to this one, right? This little 4-inch can't move nearly as much air as this for the same excursion, right? So when we get to lower frequencies, we're coming up against not an electrical power problem with PD, but rather we're coming up with mechanical limits due to X max and SD, right? So there's only so much you can do. The idea is, I'll just get a bigger loudspeaker, right? I'll go from, the 8 to a 10 or a 12 or a 15 or an 18, right? But in engineering, engineering is really a balancing game, trading things off, okay? There's going to be a trade-off there. If you go to a bigger cone, the cone itself is going to be more massive. It's going to have more mass. That makes it harder to move. That affects its transient response. It may adversely affect the efficiency. So you do one thing, you try to tweak one thing, and that has a side effect, okay? What's the overall issue that we wind up with out of here, okay? So all of these things kind of come together. Boom. That's our transducer. It doesn't matter, like I said, if it's a 4-inch or a 15-inch, that's the physics of it. Now, there's one equation you need to remember when we talk about direct radiating loudspeakers. And that is, the efficiency of that loudspeaker is equal to K, a constant I'll explain in a second, times VB, which is the volume of the box, times the lower frequency limit. Now we call that F3, it's the 3 dB down point. And that's cubed. So 3 decibels is half power, all right? So we find this lower frequency limit, this F3 or F3 dB, and that quantity has to be cubed. This equation works for all direct radiating systems. So it doesn't matter if you have something like this. Here's a little two-way system, right? We got a little woofer and a dome tweeter. This is a sealed system, okay? You can see it's just a sealed box, woofer, tweeter, okay? Sealed. Your other option is a vented or ported enclosure, right? Like this guy, okay? You put this around the back, and there's a hole here. There's actually a duct on here. It's a ducted port or a vent, okay? So we just call that a vented system. There are pluses and minuses. Why do they do that? Why would you put a hole in there, right? Hey, for that matter, why even use an enclosure? Like, what's the point of having an enclosure? Okay. Well, you don't want the front wave to meet the back wave. Right? When this thing pulses out, you get positive pressure over here, but at the same time, you get negative pressure back here. Out here, they basically cancel each other out. You get no bass. So you need to make sure the back wave doesn't meet the front wave. You could have an infinite-sized baffle, but that's not too practical. So what we do is we take that infinite baffle and we fold it back on itself, seal it up. The back wave never meets the front wave. Beautiful, okay? All right. K for a vented system is about twice the size it is for a sealed system. What does that mean? That means for the same box volume, the same enclosure volume, and the same low frequency extension, you can get like twice the efficiency. Or for the same efficiency, you could have a box that's half the size. Or keeping those the same, you could get about a third of an octave bass extension. Hey, that's pretty nice. Or you could get a little bit of each, okay? But think of it this way. This F3, because it's cubed, that's a challenge. If I have a system, like one of those small loudspeakers, and the F3 is maybe 80 hertz, right? I'm not getting really, really deep. And I decide, well, I would like to go down an extra octave. I'd like to go down to 40 hertz, okay? One whole octave, that's a factor of 2. Well, to get the same efficiency, because this thing is going to go down by a factor of 2 cubed, which is a factor of 8, that means VB, the box has to go up by a factor of 8. I need a box that's literally 8 times the volume in order to get the same efficiency. If not, the efficiency is going to get cut by a factor of 8. So you can see what the problem is. It's impossible to get a really small box that has really deep bass extension and is very efficient. You can't do all three. You can pick 2, but you can't get all 3 simultaneously, right? It's always going to be a trade-off on these things. Okay. Like I said, you can get a little bit of each. So vented has an advantage because K is bigger, so we can either go for, like I said, a smaller box, a little bit more bass, greater efficiency, which translates into higher SPL. Is there anything else that's good about it? Well, yeah. And by the way, let's do a little drawing here so we can see what's really going on. So here's your frequency. This would be the SPL. So a sealed system would give you a response like this. All right, so this corner, this is our F3. And the vented system, if I were to design it for the same efficiency in the same box volume, this would be extended out. It would go like this. And then roll off. All All right, so I get this extra extension in base. And yes, it's true, at very, very low frequencies, you actually get less bass out of the vented system than you do out of the sealed system. This roll-off is faster. On a maximally flat system, this is what we call a fourth-order curve. This is not, okay? You get like a second-order curve or a quasi-third-order curve out of this thing. There's actually a whole bunch of things you can get if you have what's called an augmented system with external equalization. But I'm just going to keep it simple and talk about these two. So you get this extra bass extension, but it does roll off faster. Here's the problem. The air that's in the port, right? You're basically exciting the air that's in the port down around the port frequency, which is VB. So VB might be over here, FB, which is like out here somewhere. Well, I'll just say, okay? So in this region around here, the excursion of the cone, the woofer cone, is actually reduced. That's good because it lowers distortion. But if we go much below that, the cone becomes unloaded, and the end result is we get tons more distortion. Matter of fact, the cone can wind up hitting the magnetic structure. It can hit the other parts of the physical structure of the frame and so forth. So that's really, really bad. I wouldn't want that to happen. So if I was going to make a little mini monitor, I probably wouldn't make it optimized for this sort of flattest response because it may not go deep enough unless maybe I had an external like subsonic filter on it or something like that. Okay. The other problem is transient response. High order systems tend to be a little bit more ringy. So if we look at a step function coming in here, so here's time, all right, just something like this, boom. For that sealed system, you're going to get a little bit of ring. You have a mechanical system, it can't start and stop instantaneously. So you're going to get something that might go like this. The vented system, it's going to be worse. It's going to have more ringing, okay? That leads to sort of a boomy kind of resonant-y sort of bass quality that, generally speaking, you probably don't want, but it's a trade-off. Smaller box, higher efficiency, better bass extension, and, the engineer sits there and figures out this or this. Let me play with this, okay? So these are all things to consider. You don't just get a catalog and say, what's the lowest FS and what's the highest PD and run from that, right? There's more to it. It's a matter of balancing these things. Okay, I think that covers it. We'll see you next time.